Hi, in the previous modules we talked about how we can model the design matrix in a standard GLM analysis. In this module we'll concentrate on the variance-covariance matrix. So recall, a standard GLM can be written as y is equal to x beta plus epsilon, where epsilon is normally distributed with mean 0 and variance-covariance matrix V. So the things that we have control over in the GLM is the design matrix X and the variance-covariance matrix V. And so the quality of our model depends on our choice of X and V. In the previous modules, we've discussed various signal and nuisance components that can be included or should be included in the design matrix in order to improve the model. And these include temporal basis function, which allows for flexible HRF shapes, parametric modulation, which allows for trial-specific variation in amplitude, and motion parameters, which corrects for spin history artifacts. There are other components that are also typically included, such as drift and whatnot. In this module, we're going to focus more on modeling the variance-covariance matrix. And it's clear that functional MRI data typically exhibit significant autocorrelation. And this is generally thought to be caused by physiological noise and low-frequency drift that's not been appropriately modeled. And typically, when taking care of autocorrelated noise in fMRI data, we typically use either an autoregressive process of order P, an ARP process, or an autoregressive moving average process, or an ARMA 1-1 process, for example. And in general, single subject statistics are not valid without an accurate model of the noise. So it's very important that we model the noise appropriately. Perhaps the simplest model that we could use is the AR1 model, and so I'm going to focus on that in this module. So we often model serial correlation using this first order autoregressive model. And here we write epsilon t is equal to phi, which is a constant, epsilon t minus 1 plus ut, where ut is normal 0 sigma squared. And so now the error term epsilon t depends both on the previous error term epsilon t minus 1 and a new disturbance term u of t, so a new noise term. So in this way, the current error term depends a little bit on the past values and also a little bit on new disturbances. So if phi is a constant that takes values between minus 1 and 1, and if phi is close to 1, then the past values are going to have heavy impact on the current value, and adjacent values are going to be highly correlated with each other. In this autoregressive model, we can study this dependence by looking at the autocorrelation function for the AR1 process at lag h. Here we can show that the correlation between two error terms that are separated by h time points is equal to phi to the power of the absolute value of h. So this is kind of a decaying function. So at lag 0, a time point is of course correlated perfectly with itself, so the correlation is 1. At lag 1, two adjacent time points are correlated with the value phi. But at lag 2, two time points are correlated, two error terms are correlated by the factor phi squared, etc., etc. And so we see this for the example where phi is equal to 0.7, that the correlation decays in this exponential manner. So we have correlation 1, then 0.7, then 0.7 squared, which is about 0.5, etc., all the way down. And so after, say, 10 to 15 time points, there's no correlation between error terms. So the correlation dies out slowly here. How do we incorporate this into our GLM? Well, the way we do this is through the variance-covariance matrix V. And so the format of V will ultimately depend on what noise model is being used. So in the simplest case, we just think of the data as being IID normal. And so in the IID normal case, V is simply proportional to the identity matrix. Actually, it's going to be the identity matrix times some variance sigma squared, which is unknown and that needs to be estimated. In the AR1 case, the variance-covariance matrix looks a little bit different, because here you'll see that we'll have 1s in the diagonal, because that's where showing the correlation at lag 0. But in the first off diagonal, it's going to be values of phi there. That's saying that points that are 1 points removed from one another, one time point removed from one another, they're going to have correlation phi. And in the next off diagonal, we'll have phi squared. That's saying that if you're 2 points away from each other, the correlation is going to be phi squared, etc., etc., etc. So this particular variance-covariance matrix captures the behavior of the AR1 process that we talked about previously. So in general, we can use this if we want to incorporate autocorrelated noise in our models. Now this becomes a little bit more complicated to estimate, because not only do we have to estimate kind of a sigma square that scales this, but we also have to estimate phi, which is the correlation between adjacent time points. So let's go back to the GLM and put this into its context. So the model we have is y is equal to x beta plus epsilon. Now we can estimate beta by computing beta hat, which is equal to x transpose v inverse x transpose v inverse y. So that's the best linear unbiased estimator of beta. Now what we want to do is we also want to estimate v now. So what we could do is we could take the fitted value, which is y hat equal to x beta hat, and compute the residuals. So that's y minus y hat, and basically we can re-express this in the following format as some matrix R, which is the residual inducing matrix, times y. And so now we can use these residuals to estimate things like the autocorrelation function, and we can estimate the variance and things like that. But you'll notice that we have a bit of a chicken and egg problem here, because we need the residuals in order to estimate v. In order to get the residuals, we have to estimate beta hat. But you'll see in the estimate here, in order to estimate beta hat, we need v. So something has got to give here. So we do we start estimating beta hat or v, and they're both dependent on each other. So in general, the form of the covariance matrix is unknown, which means it has to be estimated. And estimating v depends on beta, and estimating beta depends on v. So how do we solve this? Well, in statistics, we usually use iterative procedures to do this. So we assume a value of v first, estimate beta, then plug that value in to get a new value of v, and then we iterate. There are different methods for estimating the variance components. So by this I mean the parameters of v. And in the AR1 case, this will be a sigma squared and a phi. And these methods include method of moments, maximum likelihood, and restricted maximum likelihood. So these are three different ways of estimating the variance components. The iterative procedure that we use to solve this problem takes the following format. We begin by assuming that V is the identity matrix, and so that there's no autocorrelation between adjacent time points, and we compute the ordinary least squares solution. So that's assuming that V is just the identity. Now we estimate the parameters of V using the residuals of this model, and then we re-estimate the beta values using the estimated covariance matrix from step 2, which is V hat now. So now we can get the GLS solution, incorporating V hat in our estimate of beta. And then we iterate this procedure into convergence. We update our beta and use this to get an updated V, update our beta, use this to get an updated V, and we do this until we get a kind of a stable solution. So the question becomes, how do we estimate the variance components? Well, if we're using an AR1 process, there's a very easy way to do that using the method of moments, and this gives us the so-called Yule-Walker estimates. So in the Yule-Walker estimates, we first have to compute the residuals, and out of the residuals we compute what's called the autocovariance function. So that's basically the covariance function at lag 0, which is just the variance of the residuals, and also the covariance at lag 1. So the covariance between points that are shifted, the residuals that are shifted 1 point vis-a-vis each other. Once we've computed these entities, we have an estimate of the correlation function phi hat, and also an estimate of the variance sigma squared hat. So this is very easy to compute, and as we have a closed form solution for these two parameters. However, this only works for AR processes. If we're using more complicated processes such as ARMA 1.1, we have to either use restricted maximum likelihood or maximum likelihood. Now what's the difference between these two techniques? Well, maximum likelihood estimators are obtained by maximizing what's called the log likelihood, so this function here. Here the parameters that we want to use to maximize this are encapsulated in this function lambda. So lambda are the parameters associated with V. So in our example, lambda would be phi and sigma squared in the case of the AR1 process. So we want to find the values of phi and sigma squared that make this function, this L star, as big as possible. Restricted maximum likelihood is very similar. However, the function that we want to maximize is slightly different. This is the restricted log likelihood. The difference lies in this extra REML term, variance term. But the process is the same. We want to find the parameters, lambda, associated with v that make this function as big as possible. So what's the difference between ML and REML? Well, maximum likelihood maximizes the likelihood of the data y. And so it can be used to estimate mean parameters such as beta. However, it can provide biased estimates of the variance. So for example, let's say that I wanted to estimate the population variance of everyone taking this Coursera class. What I could do is I could take a sample of students taking the class, and those samples would be y1, y2 up to yn. And then I would take the yi's minus y bar squared and sum them up and divide by 1 over n. That would be the maximum likelihood estimate of the variance. However, that will give a biased estimate of the variance. Restricted maximum likelihood, on the other hand, maximizes the likelihood of the residuals. And this is often used to estimate variance parameters. And so these provide unbiased estimates. So in the example before, instead of dividing by 1 over n, we would divide by 1 over n minus 1, and this would give us an unbiased estimate. So because restricted maximum likelihood provides unbiased estimates of variance components, we tend to use that when estimating them. So in general, if we have an AR process, we could use the method of moments types approaches. If instead we're using an ARM011 process, which is equivalent to an AR1 plus white noise, which is often used in fMRI, we would probably use REML instead. Interestingly, the spatial temporal behavior of these noise processes is very complex. So here I'm showing the spatial maps of the model parameters from an AR2 model estimated for each voxel's noise data. So I've taken the residuals at each voxel, fit an AR2 process which has two phi components, phi1 and phi2, and also sigma. As you'll see, when you're looking at these estimates, they vary over space in a manner that has a clear spatial dependence. You can actually make out the shape of the brain here. So depending on where in the brain you are, the parameters are going to look quite different. So this is an interesting thing that if we're doing a massive univariate approach, sometimes we don't take this into consideration, but there's obviously something going on here. Okay, so that's the end of this module. Here we've learned how to model the variance-covariance matrix in the GLM, and also how to simultaneously estimate the variance-covariance matrix and the beta parameters using an iterative procedure. In the next module, we'll talk about inference. Okay, I'll see you then. Bye.